Last time we covered two topics for inducing reasoning or chain of thoughts. The STAR paper, which is self-taught reasoner, and the thought preference optimization paper, right? So today, the first was a SFT approach, and the second was a DPO based approach. This third approach that we'll talk about is a GRPO based approach. GRPO, as you all know, is online reinforcement learning algorithm. Online means the samples will come from the policy and they will be immediately used for training. So unlike DPO, where unlike the version that we saw for thought preference optimization, where you do the sampling first over all the entire data set, and then do the training, and then do the sampling, right? So GRPO is an online learning method, reinforcement learning method. And we'll see an example of a method, example of a model, very famous model that came out in January this year, that uses this GRPO with verifiable reward for inducing reasoning, and they do it very successfully, and they were able to even beat or obtain comparable performance as O1. So, and finally, we'll look at how do we induce reasoning in weaker models, because DeepSeek R10, the base model, was a very powerful model trained on a huge amount of math data. It was a 670 billion model, I think. So if you don't have such a powerful model that has been trained on such a huge amount of math data, let's say you have a Llama 8 billion or something, how do you go about inducing reasoning in those weaker models? That's what we'll look at the last. Okay, so we are all familiar with what verifiable rewards are, right? I'm talking about verifiable reward because that's what is used for inducing reasoning, because it's an absolute reward. It's not a noisy reward, and there might be a bit of a noise, but it's not a. I mean, you cannot even if you overput this reward, it's a good thing. You won't be doing reward hacking. I mean, it's not reward hacking. This reward is not a bad idea, actually. That's what I'm trying to say. So that's why we are interested in verifiable rewards, and we have talked about verifiable rewards in previous classes also. So verifiable reward means that once you generate a solution from the model using a language model from the model for a given input, you can exactly verify whether the final solution is correct or not. For math, you might simply extract the final number. Let's say it's a number, or that's an expression. You can extract that number expression and do some sort of matching with the gold number of expression that you have, right? Similarly, if you have code, you can just run unit test cases on the generated code. And we've talked about this, so I will not go into detail. And math and code is the other two things that we'll focus on for the rest of the slide. So we will keep these two only for now. Okay. Now, this is also what we have talked about. There is nothing special about inducing reasoning with GRP, actually. The only thing different from what we have talked about when we discussed GRP earlier is that now our base model is itself pretty powerful. It has seen a lot of complicated hard math problems and coding problems, right? So that's the only difference. Otherwise, and the other thing is that we are using verifiable reward. Other than this is just standard GRPO. There is nothing very interesting about it as such. So how does standard GRPO looks like? So this is a thinking model. So you will say solve this following math problem, and if you're using tokenizer chat template, you will put enable thinking equal to true. And when you give enable thinking equal to true, the model will first generate thought between think tags, and then it will generate a solution, right? So this policy is your model that you're trying to train, and it generates a bunch of thought and corresponding solutions. So but the next step is that when you are dealing with an online reinforcement learning algorithm, the next step is to compute the reward of each of these solutions. So if it is a math problem, you'll extract the final answer. So maybe the final answer is in some boxed template or some template that you specified in your prompt, you will extract that part, and then you will send it to you will compute a verifiable reward. So verifiable reward might be a binary reward. We just take whatever you extracted, it might just end the ground truth, and we'll say whether these two match or not, right? You get a verifiable reward with for each of the outputs, and now you can apply GRPO. For example, now what you will do is you will say log probability of this times the reward of this. So if you're just doing reinforce, it will look like log probability of first one times the reward of that one plus log probability of last one times the reward. But GRPO, as you are familiar with it, is that it's not a it's not fully online, in the sense that you create a rollout, you take some samples and you from a fixed policy, and then do training, and then update the policy for sampling. I mean, the policy for sampling does not always equal to the policy of training. There's some sort of lag between those two, right? So the expression is more complicated for GRPO, and this is the expression. So in GRPO, the sampling policy is, so these are all things that are already covered, so I'm not going to go into detail, but just to remind that we have an old policy from which we sample, and then we compute this RT theta equal to pi theta by pi theta old. Okay, so and y given x, and this is y given x. So this is, you can think of it as the importance weight, and we don't want this importance weight to blow up, so we clip it and then do reinforcement learning. Okay, so this is where I will leave GRPO because it's already covered. So RT theta, as I mentioned, it's the importance weight. That's the ratio of probability under the policy that you're training and under the policy that from which the samples came from. The key trick of GRPO is that the advantage of a sample is computed in a normalized way. What do I mean by normalized? If you have 8 samples, you compute the mean of those 8 samples, you compute the standard deviation of reward, mean of the reward of those 8 samples, and the standard deviation of the reward of the samples, and then you do this normalization. So this is how you assign reward to an individual output, and the idea is that if something is better than average, you want to increase the probability of that, and if something is worse than average, you want to decrease the probability of that. So reward will be, so the advantage will be negative if it is worse than average, and it will be positive if it is better than average. Okay, so we will leave GRPO at this point, and let's talk about a model that uses this GRPO and RLVR. So after this model came out, DeepSeek R10, a lot of different models like Qwen3, like Kimi K 1.5 and 2, and Grok, and a lot of different models came out who use the same approach for doing, with minor modification in the reinforcement learning algorithm, but overall approach remains same, that you collect a lot of data for which the final output is verifiable, and then do GRPO with a verifiable reward. GRPO or a small modification of GRPO. So for DeepSeek R1, they focused on math and code data, and the 0 here is, means that this DeepSeek R1 0 is that there is no SFT in this model. And effectively, all the data that you would use during SFT is already consumed during their pre-training stage. So there is no separate supervised tuning for this model, and you directly apply reinforcement learning on top of the pre-trained model, right? So the prompt of the DeepSeek model looks like something like this. A conversation between user and assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in the mind and then provides the user with the answer. So basically, it's just prompting the model to first generate set of reasoning steps, and then the final answer. The reasoning should be enclosed between think tags. The final answer is between the answer tags. And think reasoning process. So this is the structure that they have given, that you generate output of. So this is the prompt that they give to the model for training. So if you see, the chat template is very simple. User colon assistant colon is not much to a chat template, and they use this on top of a very powerful base model, which is a DeepSeek V3 base, which has seen a huge amount of math and code data. And then they use GRPO with verifiable reward. So they use for math data, they use math and code data, they use accuracy reward, and for math data the reward is simply that you extract whatever is enclosed in those boxed or whatever tags that they specify. So first they will have something like put your final answer within box or put your final answer in this format. Then they will use a parser to extract the final answer, and then that final answer will be matched with the ground truth, and the reward will be given based on whether it matches or not, maybe +1 -1 or +10 -10. So this is for math. For code, they extract the code part. So let's say the code requires you to find the shortest number in list. So there will be a reasoning step, and then there will be a small function small function that would compute the shortest number given a list of numbers. So they will extract the code part, and they will run unit tests on top of that code. So the assumption is that your code already contains unit tests that can be run. So not the code, the query already contains unit tests that can be run on the code generated. And that once you run unit tests, you will get a reward. And finally, there is a format reward because they want the model to generate output in this think tags and answer tags. So if the format looks like this, they will give a reward of +1, otherwise they will give a reward of -1. And then the accuracy reward and the format reward are weighed together, and they are used for reinforcement learning. Does this make sense? Okay. So that's it. I mean, there's nothing much about the doing about inducing reasoning using GRPO, because the approach is just GRPO on top of a very powerful base model with verifiable data, verifiable reward. And if you do that, you get this curve on this performance is on AIME. So AIME is the Olympiad level math problems from 1983. So I think this contains only till 2023, because 2024 and 2025 are used for evaluating the models. Right? These are for evaluation. So these are very tough math problems. And if you see the performance of the model at the beginning of training, so look at pass set 1. I don't remember what concept 1 is. So so this pass set 1 problem, I think, actually I don't know. So this pass set 1 initially is close to 15% or 16% or whatever, and after 7,000, 8,000 steps of training, it's 70%. So these are very, very tough problems, and solving even one problem is a huge challenge. So if you can see that the performance on Olympiad level problems jumps a lot by doing reinforcement learning. Now there can be some issue with this evaluation also, in the sense that many of the problems that you're getting evaluated against you might have already seen during training. But still, the model does improve a lot, because when you construct a huge amount of data for pre-training for math and code, you end up taking a lot of problems from evaluation. Because a lot of people might have solved a problem in a different way and put it on the web, right? Especially because these are Olympiad problems. A lot of people solve these problems all over the world, right? Okay. Another interesting thing is that the length of the responses also improve, not only the performance. So why would the length of the responses improve when we are trying to teach reasoning?
Because
Correct, exactly. So now there might be a lot of new patterns that might be emerging in its reasoning process that it would not generally do. Let's say if you would to just take the base model and apply it on a problem, it would probably solve it, and then give the answer. But now it might be doing a lot more things, and we'll see what kind of things it might be doing. It might be tracking, it might be verifying the solution, it might be exploring multiple paths, and that is the interesting part of this GRPO, this DeepSeek work. They showed that just by doing GRPO with verifiable reward, if you just keep doing it, lot of interesting reasoning trajectories emerge that would not have emerged if you had just done supervised training. If you had so a lot of patterns emerge during reinforcement learning. Until this time, actually, everybody used to think that reinforcement learning is, if you have heard of the Jan LeCun's the way Jan LeCun stated is that reinforcement learning is the cherry on top of the cake. It's a small thing that it's not the entire cake. It's not, its contribution is tiny. But when this paper came out, people realized that reinforcement learning is the main part of the cake. Actually, it is the one that can drastically make a difference in how the model. And that's what people hope still, that that we will be able to generate or create models that can actually solve novel research problems by doing reinforcement learning, right? So why do the lengths increase? As you said, there are a lot of new reasoning patterns that emerge that would not have emerged, that were not there in the starting point. And what are the patterns? Verification. Okay, I have computed an answer. Let me check. I know I can verify this answer by putting it in some equation. So let me just verify by putting it in equation. So that's verification is not something that the model generally does. Before earlier models that or before O1 came out, the models would not always verify their answer when they would generate it, right? And people also don't want all these huge steps when they generate the answer. They want the final answer. So verification was not a very common thing. Similarly, backtracking. Backtracking means that you generate a solution and then you realize, oh, I have made a mistake at certain point, and then you maybe at the third point it looks like this looks wrong. Maybe I made a mistake. Let me go back and then come up with a different solution, and then go back and come up with a different solution. So this idea of going back and keep on coming up with novel different solution for the same problem, that was also not very common in Llama models or the Mistral models from the previous year, right? So these two are important things that emerged. These two are questionable things. The sub goal setting, again, sub goal setting is basically saying that, okay, I have to solve this big problem. Let me break it into small parts and then solve each of them. This is actually, this sounds important and is actually important, but doesn't emerge very naturally in reinforcement learning. And so these two, verification and backtracking, are more emerge more naturally, at least for some problems, at least in some cases. Okay, so this is an example of DeepSeek R1's output. The question is, James write a 3-page letter to 2 different friends twice a week. How many pages does he write a year? And if you look at the question is not that difficult, but if you look at the reasoning pattern, it comes up with, let's break this problem down step by step. So this is the step by step breaking, which was there even before DeepSeek R1. But then this weight pattern, this alternatively, the model exploring alternative paths, and then verification. Is this right? Let me confirm. This is the verification. So this is back multiple solutions. Then backtracking, verification. And again, this is another some sort of verification. So very natural language, very natural looking verifications started emerging in models when they started doing reinforcement learning for very long. And that's why the responses became very, very long, like 32,000 tokens or 100,000 tokens. So this covers DeepSeek R1, and actually, yeah, okay. So I've already shown how the performance improves. Now, question is, if I just take this reinforcement learning approach, the GRPO with a verifiable reward, and I apply it on my favorite model, let's say Llama 3.18 billion, or will I get the same emergence of improvement in reasoning improvement in performance on reasoning task or not? So the answer is no, it does not. This approach, the answer is already written, which is that if you apply this approach on all models, it's not going to happen. It's not going to help. And the reason is that most of these models, the starting point, it doesn't know that these kind of reasoning patterns exist. So these reasoning patterns cannot emerge magically by reinforcement learning. The base model, your starting point, should know something about these reasoning patterns. So it should have seen those kind of patterns either during its pre-training or during its supervised SFT phase. RL is not going to make these kind of magical things happen. So this is the opposite of what we saw, that RL was bringing the magic. But now we are saying that it's true only when your model has seen a huge amount of those reasoning patterns during its pre-training or supervised SFT phase. Okay. So there was this paper which says the cognitive behaviors that enable self-improving reasoners. This is a paper that talked about these reasoning patterns that we discussed earlier, right? Okay, so they took a simple game, which required you to do backtracking and verification in order to solve the problem, right? So the game was simple, that you are given 4 symbols, plus, minus, multiplication, and division, and you are given some numbers. You have to combine those numbers to find to create the target. So you're either adding, subtracting, doing a lot of different things. Suppose I give you 24, you have to find what combination of these numbers will give me 24. So what they observed is that the models that were in which it was easy to integrate reasoning. So Quen was known that this year people tried these using GRPO plus RLBR on top of Quen, and it worked very well. So people knew that Quen it's easy to teach reasoning to Quen. So what these guys observed is that Quen can generate these reasoning patterns before you even teach it. I mean, so if you just take the Quen base model, it already has those reasoning patterns, those backtracking, those verification, those kind of things. Whereas Llama did not have those reasoning patterns to begin with. So when they applied it for the countdown task, they did reinforcement learning on this task of countdown game. They saw that the performance of Quen improved significantly, but the performance of Llama improved very slowly, and the response length actually went down for Llama, whereas for Quen it went it settled around 600 tokens or something. So basically, Quen realized that it has to use those reasoning patterns to solve this problem. Llama actually just said that I will either directly solve it or I will not solve it. I'm not going to do extra reasoning for these problems. So the length increase will not happen automatically, and these beautiful reasoning patterns will not emerge naturally. You have to teach them. So that's what I'm calling as the role of initial behavior. The initial model that you start with should have these. So if you look at this verification, Quen has 62.62. So this the average number of cases where it demonstrates verification is already 62%. So in 62% of the cases, it already shows verification, whereas Llama 3 billion only shows in 10% of the cases, and even Llama 70 billion, which is a 30 times bigger model, shows it in only half of the cases. Similarly, backtracking, Quen shows in 65% of the cases, whereas Llama and 3 billion as well as 70 billion shows in around only 20% of the cases. So as I mentioned, the base model is important. You need to have a good starting point before you start doing RL. So how do we induce these reasoning patterns? If all I want is I have a Llama 3 billion, how do I make sure that it will do these reasoning, have these reasoning patterns? And the idea is simple, that you distill the powerful model, distill the reasoning patterns from the powerful model into this small model. So you take this powerful model, something like DeepSeek R1, let's say it's DeepSeek R1. Generate multiple thoughts and solutions, verify them using the verifier, and only the cases which are verified, you use them for SFT or training. So if if you have an option that, okay, I have this weak model which does not understand reasoning very well, should I do distillation from a powerful model, or should I just do reinforcement learning on top of it? Always do distillation. Reinforcement learning is not going to help unless your starting point is already knows that behavior. So always prefer distillation to over RL in those kind of tasks. And the distillation idea is very simple, that you just take examples from the powerful model and train your weaker model on top of the examples. Okay, so this completes the distillation. This completes the DeepSeek R1 as well as distillation part. But what if there is no teacher available? Let's say you are training a model for a task and you don't have any powerful teacher trained on that task, and you don't want to go with the 600 billion model for your task. You maybe want to work with 10 billion model or 7 billion model for your task. So is there something that you can do? Can you create these patterns and train your model on top of these reasoning patterns? So you have some different problem, not math, not code, but a very different problem. Can you create these reasoning patterns for your problem and then train your model on top of those reasoning patterns? So in the next work, what we are going to talk about is how do I create these solutions that have reasoning patterns without a reasoning model, and then how do I train? Training is simple, but how do I create these patterns? Okay, so let's look at. So how do you teach a model to restart? Restart means that you are coming up with a solution and then you realize, oh, this solution is not going to work, and then you said, okay, let me try a different solution. That's a restart. That you ignored whatever, or you decided that this approach is not working. Let me try a completely different approach, right? So how do you teach restart? The idea, if you teach restart, it's not that difficult. What you will do is you will take your whatever weak LLM that you are working with, let's say Llama, and you will take the difficult math problem that you're solving. Let's say you will get multiple solutions. Some are correct, some are wrong, and then what we'll do is something called linearization. Linearization means you'll put solution 1, and then you can say, that does not look right, let me try a different approach. You'll put solution 2, and then, oh, this does not look right either, let me try this third approach. And then you will put solution 3 and say, oh, this seems correct, hence the answer is X. Yeah.
You are creating those prompts.
So basically you are prompting an LLM to somehow take these 2 wrong solutions and 1 correct solution to create this natural looking solution. We'll discuss in more detail how to do this. But somehow you have to linearize your wrong and correct solutions. And once you have linearized it, then you can do supervised tuning on top of these chains that you have created, these reasoning chains. So you can call it reasoning because it's trying multiple solutions here. So it's some limited form of reasoning. And then you can do SFT and hope that your model now incorporates this reasoning pattern. So this was one simple thing. But what if you want to teach backtracking? Backtracking means that you are solving the problem, and at the 7th step you realized, oh, there's a mistake, or this doesn't seem to go anywhere. Maybe there was a mistake in the 4th step, so let me restart from the 4th step. So you want to go back to the 4th step and try a different solution now, right? So how do you do backtracking? So this is, let's say this is a problem. A box is 2 centimeter high, 5 centimeter long, and it can hold certain amount of clay. The second box is twice the height, and something, and what is n? So now what you will do is the first thing is that you want to make sure that your answer is in steps, because you want to backtrack to a certain step. You want to make sure that the answer is generated in steps. So you can prompt the LLM that, okay, generate step by step, and after each step put double slash n twice or something like that. So it's easy to extract the steps. So you extract the steps of the you generate the solution step by step. Step 1, step 2, step 3, step 4, and step 4 you realize, no, this part is wrong, this answer is actually wrong, 480 gram is not the answer. And then so now you want to restart from a point where there was a mistake. So I think, I don't remember, so let's say the mistake was in this step. Let's say this was a mistake. So you want to start from the step just before the mistake and retry the solution, right? And maybe now you reach the correct solution. So two things: how do I get this such a tree, right? So we'll talk about this later. And now once I have this tree and I have that this solution is correct and this solution is wrong, how do I form something that I can use for SFT? So first step is that you rewrite each of the steps. So you have generated these 1, 2, 3, 4, and I've called it step 3, step 4, step 5 again, but it's I think it's fine. Yeah. So now you want to rewrite each of these, somehow combine this wrong step and the wrong solution and the correct solution. So you will, what you will do, you will prompt the LLM. You will say that given a partially thought out solution and the current step, your job is to rewrite the current step into a thought that smoothly continues the previous thoughts. So you're telling an LLM that convert this each step to actually a thought that flows naturally. Okay, because you don't want to teach the LLM that okay, this step broke and that step started. That will be difficult to teach. You want to teach it more of a smoothly flowing solution that we saw in the case of DeepSeek, right? So you asked it to rewrite the step, first step, and rewrote it. Second step, condition on the previous rewritten steps. It wrote it. Third one, and also fourth one. So here, let's say it has rewritten the 4 steps that we saw previously, LLM. And now the 5th step, we know that this solution is wrong, right? And we also know that the correct solution is that you restart from this point. For the correct solution you have to restart from this point, right? So now we prompt the LLM that this solution is wrong, this step is wrong, and in order to find a correct solution, so given a partially given a partially thought out solution which ends by identifying itself to be incorrect, you're telling the model that it's incorrect solution. The and needing to backtrack. The backtrack step says that the solution is supposed to backtrack to your. So you are given this, that the solution, incorrect solution, and you're also told that you have to backtrack to this step. Your job is to continue the existing solution thoughts by backtracking to this part. So the model, when you prompt this LLM, model will generate, oh, this does not seem right. Let me go back to where I calculated the volume of the volume of the first box. Let me go back to that point because I think that there was a mistake after that. So I will go back to that point. So it will generate something, a sort of a continuation. So basically what you're trying to do is giving a natural flow to this broken graph. If you had just put the steps there, it would not have looked really natural, right? So you're trying to convert this tree into a naturally flowing sentence. You are linearizing the tree in a way, right? And then now you can now you have the backtracking step. Now you can again use the previous prompt, rewriting of steps. So you will add the nodes of the different path, and now what you have gotten is a linearization of the tree that you can use for supervised tuning. Does this make sense? That how do you take a tree and linearize it and convert it into something that you can use as an answer for supervised training? Okay. Okay, so this was how, if you're given the tree, how do you convert it into something that can be used for supervised training? But how do I get this tree in the first place? So this paper that these slides are based on, it uses Markov chain tree search. The paper, yeah. Yeah, sure.
Every single, you're prompting the LLM to like generate each step like what separately.
So first you have the separate steps. You already have this tree, right? Here's the tree. And now the question is I know that this path is incorrect, this path is correct. Given that I have this tree structure, how do I create a natural looking solution, right?
Create tree,
not the tree. Given the tree, how do I'm prompting the LLM to convert each of them into natural looking flow, and then somehow add a flowing sentence from here to here. Basically, I am adding a sentence that will allow me to flow from here to here, and I'm also converting each of the steps into a natural looking sentence, so the entire thing looks natural. Already has the already has a tree. You are giving the tree beforehand, and then you are saying that okay, now convert it into something that looks like a proper solution. But how to get the tree is the second part, which is MCTS, Markov chain tree search. Any other question? Okay. So as I mentioned, we use Markov chain tree search for generating the solution, and the idea is that you want to generate solutions that because you can see, you can just sample multiple solutions, but they may not intersect at any point. And also you might not be able to do a very good job if you just sample random solutions. So Markov chain tree solution tree search allows you to explore high reward solutions. So it combines exploration as well as exploitation, where you try to exploit the goodness of a solution in order to decide how to construct the tree. And we will see that. So each node represents a partial solution, and the edges correspond to the steps. So partial solution means that all the steps of the solution so far, and so edges are the steps themselves, and nodes are the partial solutions. So the tree would look something like this. If I were to make the tree using this approach as is, it will say the first node would be step 1, determine the dimension of the box. The second node will be step 1 and step 2 combined, and the action would be step 2 only. So this will look very dirty. So what I will do is I will not use this tree structure, and I will use a simpler tree structure which we have been using so far, where where I will just put the actions themselves inside the node, not that partial solution. So this node actually represents the partial solution, and this node represents everything so far. So each of the node represent each of the node. So this node actually represents partial solution so far. But just like putting the step over there, it's easy to represent. Okay, and we can do that because there is generally this Markov chain tree search is used in when you're, let's say, in games, right, where there's the opponent also, or there's an environment which is stochastic. So when there's something other than the LLM in the picture, it becomes important to represent the nodes and actions edges separately. But here in our case, LLM is the only one generating the solution, and the next step generating the step, and the next state is always st plus 1 is. So if you are represent them as state s0 s1, so st plus 1 is always st times the concatenated with the action that you took. It's always a concatenation here. So we are working with a very deterministic environment where the action is just that the LLM generates is just appended. So we can do this modification of putting the nodes, using the nodes to represent actions. Okay. Oops, looks like I wrote over here. So now the question is, which node should I expand? And now let's say I'm generating the tree. Which node should I expand? And so I need to determine somehow that which node is most likely to reach the final solution. I need some way to measuring the quality of a node in order to decide where to go next, right? That's what MCTS will tell me. So how do I decide how good a node is? Let's say I was generating this tree. I generated step 1, I generated step 2. Now I want to know how good this step 2 that I generated is. What can I do? Any ideas? I mean, can I use a reward model here to determine whether so far the solution is good or not? No idea. So reward model can use. But the issue with reward model is that it's always trained on full solutions, right? Not partial solutions. So ideally I can also train something like a value function which takes a partial solution and tells you whether the partial solution is going to reach the final answer or not. We have discussed value functions earlier, and value function will also come into the picture later. But what the paper called Astro, what it does is it takes this partial solution and it tries to complete it. It generates multiple solutions completion. So completion 1, completion 2, and so on. Let's say these two completions turn out to be correct, and these two completions turn out to be wrong. So in that case, what it will do is it will assign a reward of 2/4 equal to 0.5 to this particular node, right? It's very a huge waste of time if you. I mean, it takes a lot of time. You should run multiple solutions complete, but that's. I mean, it has been shown that this results in very high quality nodes. So their aim is to generate a very high quality data for training. So they use this reward. And the second thing that you do, so this is a reward of a node. Now, how do I? So now see, I finally what I want to do is this. I want to determine that whether I should break from this point, whether I should use this node for creating a new node or this node. I need to determine the value of each node. So now I've computed the reward of this node. Can I use that reward to somehow update the value of the nodes? How do I update the value of the nodes that are previous to this node? So so if you were doing exact MCTS, you would use the queue function. The queue function basically means that given a state, if I take an action, what is the likelihood that I will reach? What is the reward, average reward, cumulative reward I will get if I just follow the policy from then on? So in normal MCTS, regular MCTS, you use the queue function, but since our states are very simple, their environment is just appending the next step to my solution. We will not be working with queue function. But in this slide, I have put this slide only to tell you that what do you do when you are working in with environment which is not deterministic. It's a stochastic environment. Okay. So this is the queue function that we'll use for our case. The value of a node is the value of all its children. So NST is the children of ST. So it's a weighted average of the value of all its children plus the reward of the node. And you normalize it. And we will look at an example how this looks like in practice. So okay, let's look at this. So let's say the reward of this node is 0, value is 0, and it has been seen only once. So n is basically how many times this node has been encountered or seen. So how many times you have passed through this node? So why do we care about n? So if you have passed, let's say, to a particular node a lot of times, that means that you have done sufficient search on top of this node. Maybe you don't want to use those nodes which you have seen a lot of times, because you want to do some exploration also. You want to explore nodes which so that will come later. But so n is the number of so this n is the number of times this state you have reached this state when you run MCTS. The state S has been selected. Okay. So if I tell you that the reward is 0, value is 0, and it has been seen one time, reward is 1 and value is 1, and it has also been seen one time. So what would be the value of our this, let's call it node 1? What will be the value of this node? It will be reward of this node, which is 0.9, plus value of this node, which is 0 times the number of 1 plus 1 into 1 upon 1 plus 1 plus 1, which is 3. So this will be 1.9 by 3. So this is how you compute. So the value of the nodes is always computed bottom up. You start with the leaf and then you backtrack the value upwards. Yeah, so this is what it is. 1 plus 0 plus 0.9 over 3. Okay, so we have talked about these steps before I actually talked about what MCTS does. And the reason is I wanted to motivate the parts which are more intuitive before we go to talk about the entire algorithm. So effectively, I have already covered how do you evaluate the node. This is just you compute the reward at each node, right? Basically, and the way you compute the reward is either you can learn a value function or you can generate multiple solutions and see how many run to completion. And we have also seen back propagation. This is just computing the value function starting from the leaves, starting from leaves, and then going upwards, right? So we have seen these two steps, which were actually the main steps. Expansion is simply means that you take the whatever model that you're using, let's say llama, you just sample the next step from a given node, from a selected node. The only part that is left is how do I select a node? How do I decide which node to select? So given if I have given this partial tree structure, which node should I select next, and then I expand it to generate a next step, then I evaluate. We have seen how to evaluate it, and then I backpropagate. So we have seen, we know how to expand, just generation, sampling the next step from the LLM. We know how to evaluate, we know how to backpropagate. But now, given that I have all this information, how do I select the node? So let's say if you were just trying to exploit the tree as much as possible, what would you do? You would always pick the, you will start, so this is your tree structure, let's say. Right? You will always pick the one with the highest value. This, let's say this is the highest value, you will pick this. And let's say this is the highest value, so you will keep on going down the tree always with the highest value, and you will end up with a node which has very high value. And that you can expand to generate a child, right? If you were doing exploration only, that means what do I mean by exploration only? That you want to always pick nodes that have not been explored much. So then you will always see you can just use this 1 over, and you always pick the node which is the highest value of 1 over nst plus 1. But this square root of nst plus 1 over over 1 plus nst1 is basically you are trying to say that this node, the answer is its parent has been picked a lot, but it itself has not been picked. I will pick those nodes whose parent has been picked a lot, but it itself has not been picked, right? So if you were to you will use some inversely proportional function of your the number of times a node has been seen if you were just doing exploration. But when you when you do MCTS, you combine both. You say that I not only want nodes that have high value, but I also want nodes that have not been explored. So you use this formula, it's this combination. This is the model's probability of generating the action or the step. So this formula is used to decide which node, at every point, which node should I pick. So the selected node will correspond to a partial solution. Then once you reach that partial solution, you will generate k possible next steps, and then you will compute the reward associated with each of those k possible next steps. And then you will update the value function, which is the, so this is the expansion phase, this is evaluation, and then you will send the reward upwards to update the value function, which is backtracking. So let's consider this example. We have two nodes. We have this small subtree that has so we have three nodes. One is the root node, and two the first step node, two possible first step nodes, S1 and S2. And here this is one step of the solution of the solution. So let's say I found that this taking this action A0 at step S0 gives me the is the better path. Let's say so the function that we saw earlier, right? What is the function? One second. This function, right? So let's say I found that this function is highest for this path. For so taking action A0 at step S0 is what maximizes that function, which is called the upper confidence bound. So I will take that node and I will expand it, and so this is the expansion phase. When you expand it, you will get two new steps, two new possible continuations. You will compute the reward of each of those two steps using whatever reward function you're using, or value, either the value function or by running it to completion, whatever way you are interested in. You will compute the reward of these two steps, and then you will update the value of all the nodes. So what will be the value of this node? Because so this node has just been expanded, you will say the value is 1, and it has been seen only once so far, and this value is 0, and this also has been seen only once so far, right? And then you will propagate this value upwards. Okay, so now given this thing, you will update the value of this node S1. So it's what will be the value of this new node? So this was the old value. The new value will be 1. The value of this 1 times its count 1 plus 0 into 1 plus the reward over 3. So this is how you will update the value of this particular node. And whatever you get here, let's say it's 2 plus 1 3 by 1 plus 1 2 by 3. Oops, where is it? You will use this value now, update v0, update v0 based on updated v1 and v2. This is your back propagation step. Okay, so now we saw, so this was just a view of how MCTS is used to create this tree structure. And we've already seen that once we have this tree structure, what we do, we find some wrong solutions, one last correct solution, linearize them somehow, and then use for SFT. Once we have this SFT model ready, now we can apply RLB. Now this becomes, so now the idea is that once you do this SFT, model has learned how to do backtracking, model has learned how to do verification. Verification, we have not seen how to add, but it has learned how to do backtracking, right? So now we can apply GRPO. And once you do that, you see that as you do reinforcement learning on top of this model, at the starting, let's say there was the number of backtracks was only 1 on Math 500 dataset, but after, as you continue training, the number of backtracking behavior increases quite a lot. And this is the performance. So the other, so now if you, now this is the comparison, that you could have taken the model and directly done supervised tuning on top of without linearizing those traces. You could have just picked the correct solution and done supervised training, right? And then did the reinforcement learning. So one is you created this linearization of traces. The other is you don't do linearization, just do MCTS, pick one correct solution with the highest reward, and do SFT and then apply RL. So that is your direct SFT. So there is a 4-point difference between direct SFT and S2. So S2 SFT is where you create these reasoning chains and then do SFT. So in both the cases, you are doing MCTS, you are still doing MCTS. The difference is that whether you are linearizing, so this is non-linearization, you're just picking the correct solution. Pick the correct path. You just pick the correct path and then do SFT. So if you do that, your performance on Math 500 is 65, on AMC is 45, and 16.7 AI. And if you do S2SFT, there is improvement, and not so much improvement here. But after RL, both of them improve. There is somewhat more improvement with linearization. So actually, I wanted to cover this paper because I wanted to. This has MCTS explained in a well way, so it will be good to know about MCTS, Markov chain tree search. And yeah, I think that's it. Let's stop at this point. So this is the paper. This one is a paper that talks about Markov chain tree search, the one that I covered here. And we also covered these two papers here, and the first three papers we covered in the last class.